Okay, hey there. Going to be talking about the shape operator today. The reason I'm actually going to be making a video on it is because for some reason it tripped me up, and it took me a while to actually like see what's happening. I mean, it could be obvious to other people, but for me, it took me a while. And it's because I'm not actually familiar with the shape operator. It wasn't until this year I actually heard about the shape operator. You can get curvature, you can derive the Riemannian curvature tensor, and the Ricci curvature. Oh, sorry, not Ricci. It's Ricci curvature tensor, and all that stuff. Just using just a bunch of different ways to actually get them out. So one way to go about it is talking about Gaussian curvature and how you can actually get Gaussian curvature. And let's see how it's an intrinsic property of your curves and surfaces is by going through what we call the shape operator. So that's what my journey was. And for some reason, it took me a while using the notation of where I learned it from to actually get it. So there's a bunch of notations out there. So I'm going to be using the notation I learned it from and why it maybe confused me and hopefully helps some other people. So as much as I would love to build up the shape operator from, from starting with like what does it mean to be exterior derivative, what it means to be a wedge product, what it means to be a one form, et cetera, et cetera, et cetera. I am going to assume that the viewer can follow along with my notation. It's actually pretty easy stuff. So the first thing we're going to start off with is what it means to take a derivative of a unit vector or a basis. So I'm going to write out the abstract notation and I'll describe what it means in a second. So I think off the top of my head, this is what it should be. Let me just check my notes. I'm pretty sure this is what it is. Yeah, this is. Okay. So what this means is I take the derivative of some unit vector. I'm going to get out some connection, and that connection can be multiplied by another unit vector. Now, the connection is a derivative of itself, as we will see in a moment. It usually represents a one form, and to pull this like out of abstract concepts, let's start off with saying we're working in rectangular coordinates. So remember, rectangular coordinates are just regular x, y, z. So in this case, we would have our basis of E1 orthogonal means this would be orthogonal basis. It's not 3 yet. It'd be an orthogonal basis, which just means they're all perpendicular to each other. E3, yeah, my handwriting's really bad and my E's get bigger. And I can't even do my curly brackets on this. Okay. So I wish I had something other than paint, but I do not. And this is equal to x hat, y hat, and z hat. All right. So basically what this is telling me, let's say I pick j to be 2, right? Then I would have the equation d e2 is equal to w I 2, because I pick my j. So you have to pick something. So I'm going to pick it to be 2, because I want to see if I take my derivative of my y hat, what do I get out? So this tells me I pick it, so I make my j 2, and then over here I have this. Now, what Einstein did a long time ago, this is called Einstein notation or Einstein sum notation, whatever you want to fancy calling that. Basically, what this tells me is, look, buddy, I got a 1 and a 3. I still have to compute, right? So this I can either be 1 or 3. So I'm going to write this as W1, 2, e to the 1. And still, this I can also be 2, right? Just because my j is 2 doesn't exclude my I from being 2 as well. So I have to put that in here because it has the possibility of being it. And then my last one is 3, 2, 3. So that tells me if I take the derivative of the second component in my orthonormal basis, this is what I should get out. And that depends like on how many dimensions you have, et cetera, et cetera, et cetera. To put this into less abstract terms, this is equivalent to saying the derivative of y hat is equal to w of x, the connection of x and y, times x hat, plus the connection of y to y, which is times y hat, plus the connection of z y z hat. So I mean, these two notations right in front of you are the exact same. Okay, they're the exact same notation. So that's something you have to notice. But then you have to think to yourself, okay, buddy, thanks for telling me that. Cool, great. But how exactly do I get this? How exactly do I get this? How exactly do I get this? This notation is useless to you unless you use the things we call the torsion-free condition and the metric compatibility condition. Basically what those are is, let me just select everything. I don't know, quickly deleting it, but this is the easiest way for me. So let me just write out our first condition. The first thing we need to notice is 1. D is equal to W. Actually, let's just change it. Let's say this is just so we can, like, you know, see what it happens. This would still just be W, K, this. Sorry, oops. I'm so bad at this. Sorry, people. Okay, cool. And now our second condition is I make the argument that, and this one I'm not going to actually prove. This one, just take my word for it because I don't want this video to go on forever because it's going to be a long video anyways. Just you have to take my word for it. I can make the argument that Wji plus Wji, sorry, Ij for this one, the connection of Ij and Wji is equal to 0. Now this is what it means to be metric compatible, because this would then imply that Wij is equal to negative Wji. Okay. Now this is very important. We have to realize that this is the case. Okay, I would just take it for now. If you need an explanation, I can maybe upload a different video or just look up metric compatibility, you know. So, let's see. The last one we need is, this is our torsion-free condition. Now, once again, I'm just going to give it to you guys. You can look it up on your own for proof. I just want to talk, like, we're just going to talk about the notation. You know, that's what I did before. That if you have, for example, we have to sum over the i's here, sum over the i's here. Here we have nothing to sum over. You see, if I pick an I and I pick a j, then these, I have to pick them. You know, there's nothing to sum over. This one is just, you have to pick an I and a j. And for the last one, this is what we call a torsion-free condition, is the differential, the derivative of my one form plus my connection, what is it? Is it Ji? I think it's, no, it's I. Is it Ji? Nope, it's Ij. So it's Ij wedged with my one form in the J component. I believe so. Let me just look real fast. It should be. Yeah. Okay. So, yep, okay. Just making sure. So, as you can see here, I have to pick which basis I'm differentiating first, right here. So this is how you start this one off. You say, okay, let's just say, let's move on to spherical coordinates. So in my spherical coordinates, I would have, so let me just move down here. So let me see what I can do. I can just do this. So these are the three equations we want. And then I'm going to be working with the line element ds squared equals, so we're going to be working in spherical coordinates, okay? So we would have ds squared equals dr squared plus r squared d theta squared plus r sine, that's our r squared sine squared theta d squared, which would give us the basis of, let's see, it would just be dr comma r d theta, sorry, that's r is bad, r d theta comma r sine theta. Okay, there you go. So this is the basis we're working in, right? So this right here, this sigma correlates to one of these. This sigma correlates to one of these. So I can write this as 1, 2, 3. This is sigma 1, this is sigma 2, and this is sigma 3. These are equivalent notation right here. These are equivalent notation. So this is kind of standard differential geometry stuff. It's not even differential geometry. This is standard notation for this field. It's not even differential geometry. It's just standard notation for this field that we're summing over these stuff. So the sum is standard notation. I'm not necessarily sure this is standard notation. I'm pretty sure you could bring tensors into it and whatever. So there's a bunch of different ways to do this. So now we have this. So now we are building up the shape operator. We're going to get there eventually, so don't worry. So let's do it like this now. So I want to say, what is the derivative if I hold, we're going to hold r constant. So if r equals constant, then dr obviously equals 0, right? Because the derivative of constant is 0. So remember that. So I'm holding r constant in this scenario because I want to get to the shape operator like ASAP. So I'm going to hold r constant, and basically what that's saying is, like, if I'm on the surface of a sphere, I'm holding my r constant. So basically what we're going to have then is we are going to have d of sigma 3, equals 0. So remember, I'm using this equation right here. Okay, so I say the derivative of my third orthonorm, my third one form, or my third basis, is equal to 0. Well, all of it is equal to 0. We'll walk through it. So I'm bringing this down here. So I said I equals 3. That means when I sum this out, all my i's equal 3. So I'd have 3, 1, wedge, and my j's have to match. So I'd have sigma 1. And since it's a sum, I have to sum it out. So we have sigma omega 3, 2, wedge 2, and then I'd have omega 3, 3, wedge sigma 3. So that's our first one. But remember, we still have 2 other bases we need to look at, right? We don't really need to, but for this video, I will do it anyways because it's good to just get practice down for other ones. So then I can say the derivative of my second basis is equal to 0 plus, well, it's not equal to 0 in this case, and we'll see why in a second. So I let my I equal 2, and therefore let's get summing. So in this case, my j is 1, my I is still 2, but my j is 2 in this one, and my I is still 2 in this one, and my j is actually 3. Is there any way to like make this bigger? Yeah, there we go. Nice. Okay. So let's bring it down here. I would have 0, and then for my last one, I have to take I'm gonna come back to this in a second so we can change this up real fast. So then my last one is d sigma 1 plus no, that's fine. I'll just leave it like that. So then in this case, I'm choosing I to be 1. So we would have 1, 1, wedge, sigma 1 plus 1, 2, wedge, sigma 2 plus omega 1, 3, wedge, sigma 3. All right, so cool. Great, I have a bunch of abstract notation now. Like this is easy to write out, but it's kind of hard to see like what do my omegas equal, right? So basically, we're looking at the ones using the condition number 2. So remember, number 2 is our metric invalidity condition, and this is our torsion-free condition. So I can solve, right? Because in this scenario, these are actually 0, right? Because, in other words, if I have omega 3,3 equaling negative omega 3,3, the only way that actually comes out is if it's 0, right? A negative number, the only number that's multiplied by a negative number that equals itself is 0. So that's why 1, 1, 2, 2, and 3, 3 all go to 0. So that makes our equations way easier, right? And what else makes our, yeah, let's do this. What also makes our equations easy is the fact that, actually we're not gonna do that yet. So we're just gonna solve it now. So for the first one, we have 0 equals d of omega 3. So remember, omega 3 in this case is r sine, sorry, I put a d phi up here, r sine theta d phi. So we have to take the derivative r sine theta d phi plus omega 3, 1 wedged, and what's omega 1 in this case? Well, it's just dr plus omega 3, 2 wedged sigma 2. Well, what is sigma 2 in this case? Well, it's just RD theta. So we're just going to put that up there. All right, and then for our second one, we have 0 equaling to the derivative of omega 2, sorry, not omega 2, sigma 2, which in this case is r d theta. And then once again, we would have a 2, 1 wedge sigma 1, which is dr, plus omega 2, 3 wedge r sine theta d phi. And essentially how you should like realize is the thing in here, you should not have any, you see our differential right here? This differential should not appear in any of these, in any of your omega terms over here. So like, that's not for the till we're done with the problem. For when you're setting it up, this differential for an orthonormal bases should not be appearing over here. So that's how you know if you're messing up, is right there. And then for our last one, we have d of dr plus omega 1, 2 wedge r d theta plus omega 1, 3 wedge r sine theta d phi. All right, cool. So we can now, if I take this out now, cool. So these are the equations we're working with, right? So let me take my derivatives now. So let's just expand out my derivatives. So I have 0 equals, if I expand this out, I have 2 product rules. So I would have sine theta dr wedge d phi. Because I take the derivative of the r term, I would just get 1. So it'd just be dr wedge d phi. And then if I take the derivative of cosine, I get r cosine theta d theta, because I took the derivative of theta, wedge d phi plus blah blah. Actually, I'll just write it out. I won't be lazy because some people might need that. So I will just take this and move it up here. So let's zoom out a little bit so we can see that. And then I would have 0 equals, and then this is for this term. So, oh yeah, also I should probably put up here, the fourth one is d squared of any basis is equal to 0 in this case, okay? In orthonormal basis, we can assume this. If your basis is not orthonormal, you can't necessarily assume this. But for now, we're going to assume this. So that's why if you look at when I differentiated this, you're like, wait, you forgot this differentiating the d phi term. Well, d squared phi would just be 0. So the whole thing would just go to 0. So the same with down here. We only have a dr wedge d theta because the differential of this just goes away. So then we have dr d theta plus this now. Hopefully I didn't make a mistake because that would be, actually I'll just write it out because I might have made a mistake. So then we would just get W21 wedge dr plus W23 wedge r sine theta d phi. So I can delete these now because I don't need these poop equations anymore. Cool. And the last one, we're going to get 0 equals 0 because the differential of this goes away, and then we're just left with our omega terms. I'm so sorry for my handwriting. It's pretty hard on this. I wish I had like I'll probably type up a LaTeX document to correspond with this video for those who need just a quick one, who don't need to like watch and walk through it. So anyways, as you can see, this would go away. So, great. Cool, Ramin. How do you actually solve anything now? You know, you gave me a bunch of equations, but like, how do I actually get my omega terms to mean anything? Well, remember that this one I added really late, that I probably should have added first, is the derivative of any one form, the second derivative of any one form is equal to 0. We can also use that to help us to say that a derivative wedged with itself is equal to 0. So, going down to this simple one, I can look at this omega 1, 2 wedge RD theta. Well, I know in this case that to make this whole equation equal to 0, I need my omega 1, 2 term to include a d theta term. So for now, I'm going to say omega 1, 2 is equal to a d theta. And I say for this term, well, if this is 0 now, because my omega 1, 2 is equal, my omega 1, 2 is equal to a d theta, this goes to 0. And I want this to also go to 0. Well, that means I can ignore this stuff out here. I just care about my differential. So I can say, well, cool. To make everything equal to 0 here, I need my omega 1, 3 to equal to some b d phi term. Cool, cool, cool. That's great. So now my last equation is solved. The last equation, I've solved it. It works out. This is for my dr term. So now we're going to incorporate our metric compatibility to showcase that, well, if omega 1, 2 equals a d theta, that should imply that omega 2, 1 is equal to negative a d theta. And that should mean my omega 3, 1 is equal to negative b d phi. So let's go look for our omega 2, 1 term. So we go up here and we say, okay, if I plug in omega 2, 1 up here, so Let's do that over here. So if I look at this term, I have omega 2, 1. So I'm going to come up here and I'm going to write this out as 0 equals dr wedge d theta plus, well, in this case, minus, because I'm just, for right now, I'm assuming it's a minus. So I'm going to say minus a d theta wedge dr plus omega 2, 3 wedge r sine theta d phi. Cool. So this right here has a d phi term and doesn't have an r term, a dr or a d theta. So this one by itself, I can just sit here and I say, for some c d phi, this goes to 0. So I don't want to deal with this right now. But we're going to come to it later because we'll have to use it for the big mama equation at the top. But let's deal with this for right now. So I see I have a dr wedge d theta, and over here I have a d theta wedge dr. So I need to recall that I can switch, I can put my dr over here, but I have to add a negative sign. So that's what I want though, because I want to say dr wedge d theta minus a dr wedge d theta should equal 0. They cancel each other out. So I'm going to do that now. So I have 0 equals dr wedge d theta. But remember, I have a minus sign already, so this would be plus a dr wedge d theta. And since this already went away, I'll just say plus 0 for now, because I said omega 2, 3 equals c d phi, so this is 0 right now. So in order to make this equation true, a would have to equal -1. So that would imply, going back over here, that this equation, W12, is equal to negative d theta, comma, W21 is equal to d theta. Cool, that's what we needed. We did it. And remember that W23 is c d phi. We still solved it for c, and W13 is b d phi. We still haven't solved it for our d term yet. So I'm just going to delete this all. I'm going to delete this over here now. I probably should delete that. I'll delete this now. So this will be my workspace over here, I guess. I'm so bad at this. Fuck. Okay. Yeah, this probably is not the best video presentation, but whatever. It's just for me and for people who want to sit through it and learn it. Okay. So we know that W12 equals negative d phi, d theta, W21 equals negative, sorry, W12 equals negative d theta, W21 equals d theta. We know 23 in this case, because it was our second equation, so it'd be W23 is equal to some c d phi, right? So now we have the big mamba up top. I'm going to separate it into two things. So I'm going to have 0 equals sine theta dr wedge d phi plus r cosine d theta wedge d phi minus b d phi. So why is it minus b d phi? Because remember I said 1,3 is equal to b d phi. So that means if I flip my components, I get a negative sign. So I'm flipping my 3 and 1, so I should get a negative b d phi. So I'm just substituting my negative b d phi up here, wedge dr, and then the same for the minus one. I said my 2, 3 is c d phi. Therefore, I should have a minus c d phi up here, wedge r d theta. So we have good news and bad news. The bad news is, just looking at these right here, the d phi, is that d phi? Yeah, d phi wedge dr doesn't go away. and my d phi wedge d theta doesn't go away. So I have to use the ones up here. And then there's the good news. I can see my sine d theta d has this term as a dr wedge d phi. So, okay, I have a d phi dr down here. So my b is probably going to be canceling this out now. Then I can see I have a d theta d phi term. Cool, I have a d phi d theta term down here. So I just need to switch everything around. So I'm going to do that now. I'm just going to erase it. So I'm going to change my r over here. So I'm going to write this as r, and I'm going to write this one as phi, because I switched them around. But by doing so, I would need to put a negative out front, which would make this positive, and same for over here. I'm going to change this to a phi, and I'm going to bring my r with my theta too. You don't need to. You can always bring things that aren't differentials to the front. So technically I should always have the r out here, but I didn't. And now I'm going to bring this out here, and this should be a plus. Cool. But we still need to solve for our c and b terms. Well, to make this equation 0, I would need my b to be a negative sine theta to make that go away. And then, so let's see, sorry, equals b. And then for this one, I would need to make this go away. Well, I already have an r, right? So I don't need to have an r term. So I should just make it a negative cosine theta. This would make this equation go away because my d phi, I would have a d theta, d phi, I could factor that out, and I would have r cosine theta minus r cosine theta, 0, anything times 0 is 0, even for differentials. So I should make r cosine theta equal to c. Great. So now I have all my omegas, right? So let me just write out my omegas real fast. I'm going to write them over here, so this goes away. So let's write them out. So I say omega 1, 2 is equal to a d theta. But remember, a equals 1. So I just have this, equals negative 1. So this would be negative d theta. I have omega 1, 3 is equal to b d phi. So I can say that omega 1, 3 is equal to negative sine theta d phi, and then my omega 2, 1 is just the negative of this, so it should be d theta, and my omega 2, 3 is equal to c d phi, and c is equal to negative cosine theta, so this would be negative cosine theta d phi. And last but not least, last but not least is 3, 1 is just a negative of that. So it should just be sine theta d phi. And then my omega 3, 2 is just the negative of this. So it should just be cosine theta d phi. So an exercise for you guys would be to go back into your expanded torsion form and plug in these omegas and see if you actually get out 0. I think I wrote everything down right. Possibly I didn't, but we'll see. We'll see once we get to our shape operator anyways. So now I have my omegas. I can actually delete my torsion form now. So I'm going to delete all this. Great. So here are my omegas up in this corner. Okay. So now we have our omegas. Great. Great for us. So now we're ready for the shape operator. We solved our omegas. Finally, it's a long process, I know. There's easier ways out there, but using the notation, this is how you solve for your omegas. So now we're ready for the shape operator. So on the surface of the sphere, I can make my r constant. So I'm going to do that. So I'm going to say my omega 3 is equal to 0. And the shape operator tells me that I have a matrix S is equal to the negative of my Christoffel symbols of I and J. Now, okay, you might be wondering, okay, buddy, you just made me solve for omegas. Is there a connection between our connections, our omegas, and our Christoffel symbols? And yes, there is. And this one I'm not going to justify either. There's many proofs out there on the internet. If you need one, just look one up. I can make the argument that Ij is equal to up here should be I, and down here should be J, K. Or in this case, I could, how do I do this? I'm going to make this so I can line up with my notation over here. Okay. So I'm going to say omega kj is k ij sigma j. But in this case, as you can see, I am picking my k. So this forces omega 3i to equal my Christoffel symbol, where we pick our I and we sum over our j's. So, finally, we should get that my matrix should give us this. So our matrix S should be this. As you can see, we only have 4 terms. We have 1, 2. So we have 1, 1, 1, 2, 2, 1, 2, 2. So this S is equal to negative Christoffel of 1, 1 for this place in our matrix. Sorry, oops, that should be 2, 1. 2, 1, and finally 2, 2. Alrighty. So now all we have to do is solve. So let's do the first one. We have R3. Sorry, oops. Let's write it out better. So we're gonna be using this over here. So we would have omega 3, 1 is equal to gamma 3, 1, 1. We would have sigma 1 plus gamma 3, 1, 2, sigma 2. And then you would say, okay, cool, I should have a 3, 3. I mean, 1, 3. But remember, on our surface, we said our x3 was constant. So that makes our 1 form equal to 0. So we have no sigma 3 on this surface. It's equal to 0. So I don't need to write out my last term, which would be gamma 3, 1, 3, omega 3, because it's just equal to 0. So now let's just plug in everything, and we should get gamma 1, 1. In this case, sigma 1 is equal to, ooh, I messed up. in this case, I have to make sigma 1, sorry. I'm making sigma 1 equals 0. So this, sorry, I need to fix this real fast. Okay, for this one, I'm switching these around, my bad. So, dang, did I mess up? Yeah, I messed up. So we're gonna make this 1. Actually, let's just make this easier on ourselves. I'm making R constant, so this should be sigma R. So anything that involves sigma R is going to be that. And then, so in this case, I would have, I'm going to make this sigma phi plus gamma 3, 1, 2, sigma theta. Because I don't want to know sigma R, okay? That's all I'm saying. I don't want to know sigma R. And W31 in this case, or R1, yeah, I messed up. Whatever. If you got this far in the video, great for you. You should have realized a long time ago that I messed these up. In my notes, I have these switched. So my dr and my phi terms are switched. So in this case, it's just omega r phi. So in this case, we have omega r phi, which is what we want right here. So we have that. So this should be sine theta d phi. Okay. And then we would have this. So and then I'm going to plug in our omega phi over here and my omega theta over here. So this is R. Let me just crop this out. Actually, I'm just going to do this now. This, my gamma 1, 2 is going to be 0. And the reason for that is going to be 0 is because if I hold something constant on my surface, then I'm going to have if I hold something constant on my surface, eventually what I'm going to get is that my gammas, a bunch of them cancel out because my omega 3 or my omega r in this case is going to cancel out. So a bunch of them cancel out, and all I'm left with is gamma 3, 1, 2 is equal to gamma 3, 2, 1. So they're the same thing. And what you will see is that I have a d phi term over here, and I would have a d theta term over here. The only way this could ever be true is if gamma 3, 1, 2 is equal to 0, right? I need these to be equal to each other. This has to go to 0 in that case. It just makes this is the easiest thing to do. I'm pretty sure you could find something convoluted and say, well, it's not equal to 0, but that's the easiest case. So we're just going to assume it equals 0 in this case. By saying that equals 0, that also implies that omega 3, 2, 1 equals 0 because they're the same thing. So I'm left with omega 3. So I have sine theta d phi is equal to all of that. So, which is cool. And sorry, I'm just looking for my notes real fast. Like, make this a bunch easier so I don't make any more, typos like I've been up here that I was doing. So we get omega 3, 1. Yep, that's right. And apparently I got this backwards. I should have a negative sign here. And I should switch these. So these should be pluses. And can't go back and fix that. So I'll edit the video and fix that for us earlier on. But I should have a negative here. And the only way this could be true is if gamma 3, 1, 1 is equal to negative 1 over r, right? Because then that would make this negative over here, and that would cancel off the r. So gamma 3, 1, 1 is equal to negative 1 over r. So I have negative 1 over r here. I made the argument that this should be 0, so I'd have 0, 0 here. And then for our last one, I should also have a negative on my 2, 1. So I have my 3, 2. So this should also, where's my thing? This should also be negative, I think. Yeah, that should also, where is it? Oh, did I mess up? One second. So this is saying my r theta, because I made theta equal to, so my r theta. Oh, sorry, in this case it's not 3, 2. In this case it would be 1, 2, right? It'd be 1, 2, so I have that up here, so that's fine. In this case it would be 1, 3. So I had it right, never mind, I had it right. My bad. See, I messed up my notation and my notes and then up here, so this is fine. And so we would have this, so that's all I have to do. All I have to do is I'm holding one constant. So this would be 1, and this would be 1, 3, and this would be 1, 3. It happens, folks. We all mess up. So that's how I have this negative out here. I have this negative out here because I'm holding my r constant. So I'm using this term over here. So that's how we get negative 1 over r. That's all right. That's all right over here. All right, and then finally, I have my omega. Sorry, I have to leave this to be 1. So I have my 1, 2. Really changes everything, right? In this case, my S matrix is 1. And then down here should be 2, 2, so 2, 1, 2, 1. So let me just rewrite this as S equals negative gamma of 1, 2, 1, gamma of 1, 2, 2, gamma of 1, 3, 1, and gamma of 1, 3, 2, 1. And so we already solved that 1, 3. In this case over here is not what we want. So it's ij. So I pick my I. So I would say 1, 3. So yeah, this would be, so this would be 2, 2, 2, 3. This would be 3, 2, 3, 3. So I've picked my omega 3, 3 to be 1 over r, negative 1 over r. And then in this case, we're going to solve it real fast with no mistakes. So you can see it like this, and we get, so I pick my I to be 2, so I get 2 omega 2 plus gamma of, by habit. See, by habit, you always make your third equal. So I did that by mistake. And then this becomes Q3 omega 3, but this goes to 0, and over here I'm left with negative d theta is equal to gamma of 1, 2, 2 make it 2. In this case, it's RD theta. And the only way to make this equation true is if gamma 1, 2, 2 is equal to negative 1 over r, right? Because the r's are canceled and make it negative d theta equals negative d theta. So I have negative 1 over r over here and 0, 0 over here. Great, that's what I wanted. So I did my calculations, that's great. So what does this actually tell us? Well, for the most part, on a sphere, we see that we have curvature in 2 directions, right? Which doesn't surprise any of us, right? Basically, if I have curvature in 2 directions, that's what a sphere is, right? Because I would have like, it's like this, you know, I'm curving like this, you know, I have curvature in 2 directions. Now, if we were to compare this to something like a cylinder, which you should do if you want to check it out, I'll probably make a video on that too. For a cylinder, our basis is, just to make it easy on ourselves, my basis for cylinder is dr, comma, dz, sorry, that's a bad z, comma, r, d, theta. So it's just polar coordinates, and you have third dimension of z. So you will see for this one, your answer will be 1 over r, 0, 0, 0, because we only curve in one direction. In other words, I can make a cylinder by just curling my paper in one direction, right? I can't make a piece of paper turn into a sphere without ripping it, because I can actually make a sphere by like going in 2 different directions. You know, I would actually have to rip my paper. So the other thing you will see from your shape operator is that if I find the eigenvalues of this, you get something called Gaussian curvature. And now Gaussian curvature, to be honest, I don't really know what it is yet. Just kidding, I do. Let me just reference my notes. It's an intrinsic property of your surface. So what does intrinsic property of your surface mean? It means it doesn't matter what dimension it is, it's always going to curve this way. You'll see that other properties are what we call extrinsic curvature, and this is what I think. I could be wrong. This is what I think. I think intrinsic curvature tells you that this is how your surface or curve, whatever, sits in R3. This is how it looks in R3. So, in other words, I'm pretty sure that means, see if I have any better notes. Not really. So yeah, that's all it really means for me. So let's just get our last calculation out of the way, is define our Gaussian K1 and K2, right? So we can just walk through that. So I'm going to delete everything else over here because it's not needed right now. So we have our matrix. So we have our S is equal to 1 over R, 0, 0, R, diagonal matrix. I'm going to find the eigenvalue. Let's do this. So the first thing I do is I need to subtract it from an identity matrix multiplied by lambda. So I get lambda and lambda 0, 0. And after subtract these both, I get a matrix that is 1 over R minus lambda. And over here, I would have 0 minus 0, so 0, I have 0, and I have 1 over R minus lambda. Great. Now, I need to take the determinant of this and set it equal to 0. So the determinant of our matrix over there. And I could have used better notation, to be honest. I could have just gone like this, but it is equal. So we're going to say S, comma, not comma, because that means derivative in most places. So we're going to go S, comma, we'll just do that, is equal. So I need to multiply this, and then these are just 0. So I get 1 over r squared minus, I would get lambda r minus lambda r, so minus 2 lambda r plus lambda squared equals 0, right? It might not be obvious what lambda would be in this case, but if I just look at it, right, I want to make this equal to 0, so I can notice that, hey, if I say lambda equals 1 over r, what do I get? Well, let's just see. I get 1 over r squared minus 2 over r squared plus 1 over r squared. Cool. One of these r's cancels one of those, so we have that, and then I have negative 1 over r squared plus r squared equals 0. Check. So my curvatures are lambda, or sorry, in this case, K1. So this is your Gaussian curvature. As you multiply your two eigenvalues together, you get K1 times K2 is 1 over r squared. So we have a non-vanishing Gaussian curvature, which means we have an actual curvature because we can't create this sphere from a flat space. And then let me just delete everything else because there's some other stuff I should probably tell you that you can get from this guy. Is we have another property called the mean curvature. The mean curvature is just the trace. So in other words, it's just K1 plus K2 in this scenario, which would just be 2 over r squared. And then last but not least, actually I'll just close this real fast. There's another one we can get out of this, but I don't know it off the top of my head. So let me just see my notes on my computer if I can ever find it. Oh, this video is long. Let me see if I can ever find it. There we go. So we have our Gaussian, which is this. And nice. Let me just do it on my phone. We would have a, what's the last thing? Fuck off. Sorry. So these, the K1, K2, that's the last thing I should have specified earlier. The K1, K2 is actually called the principal curvatures of the surface. And these K1s and K2s give you the maximum and minimum curvature through a point. So this is your Gaussian, this is your mean, and this is your maximum and all that. So once again, you should try it for yourself in cylindrical coordinates, and you should get 1 over r 0, 0, 0. And you should see that your Gaussian curvature in this case would just be 1 over r, comma 0, so then it vanishes. So that means you can create your surface from a flat space. That's all I really have for now. The video is probably bad, but it's my first one, so peace.